optimization problems. We're getting into the meat of the uses of derivatives here, what the real life applications. This is where I get excited. This is what my thesis was about. Optimal control means that we're finding the optimal value, the best answer for a situation. So usually we're given something that needs to either be maximized or minimized. So our first step is to determine the quantity that is to be optimized, that is to be maximized or minimized. The second step is going to be to draw a picture. Define variables. Next step, we're going to write a primary equation. Equation representing the quantity to be optimized. If the primary has more than one variable, a secondary equation is needed. To be substituted in. So we have only one variable. You remember substitution. We're going to use substitution to get it back down to one variable. Once we have only one variable in our primary equation, we're going to take the derivative of the primary equation. To find the max or min, depending on which one we needed. That's our steps. So we really need examples. So this first one, a manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with maximum volume? So we're trying to maximize volume of a box. So the first thing I'm going to do is draw a picture. We have an open box. It says it's an open box, so it does not have a lid on it. It said it had a square base. So this base down here at the bottom is a square. So I'm going to call this side x and this side x. And just for fun, I'll call this h for height. Okay, so the volume would be x times h. Now notice I have two variables, x and an h. I only want one. So I wonder if something else that they gave us would be helpful. Well, they did talk about the surface area, right? So I'm going to come off to the side. They told us that the surface area was 108. Well, what makes up the surface area of this figure? Well, you have the base here, which would be x squared. And you have 4 of these walls. And each of the walls is going to be x times h. Now, remember, I'm trying to get this where it only has one variable. So I think replacing that h is going to be the key thing. Get them all where it's just x's. So I need to rearrange this where h is by itself. So the first thing I could do is subtract the x squared. And then divide by 4x. So this is the secondary equation, and it's rearranged for h. So that now I can use substitution and replace that h with what h is equal to. So that's really x squared. And then this is 108 minus x squared over 4x. I think we can clean this up a little bit. Let's see. Can I divide each of these by 4x? See, 108 divided by 4 is 27x. And x squared divided by 4x is going to have an x in the numerator and a 4 in the denominator. Now I'm going to distribute the x squared just because it'll make it easier. X squared times 27 over x is going to be 27x minus, that's really 1/4, x squared times x is x cubed. We want to maximize volume. So now I need to take the derivative of volume. And I got 27 minus 3/4 x squared. Now to figure out what values are maximum in this case, I need to set this equal to 0 and solve it. Well, let's see, that's going to be negative 3/4 x squared equals negative 27. If I multiply by negative 4/3, that's going to leave me with x squared equals 9 times 4, 36. Oh, that's nice. Now, normally, I'd have x equals plus or minus 6, right? But could x be a negative 6? No, it's only going to be a positive 6. So I need to see if that 6 is a max or min. So if I pick, let's say, so we're going to start at 0 because it wouldn't be anything else. So if I plug into the derivative, let's say I plug in 1. 27 minus 1, that's a positive. And if I plugged in something really, really, really big, I would end up with a negative answer. So positive to negative, v prime of x changes from positive to negative at x equals 6. So what does that mean about 6? 6 is going to give me a maximum volume. So what did it ask for? It asked for the dimensions. So the dimensions are, we're going to have 6 by 6. Now how would I find the height? Oh, look at that. So I'd have 108 minus 6 squared divided by 4 times 6 gives me a 3. What is the maximum volume? Well, the maximum volume, remember, is x times h. So 6 times 6 times 3, which is 108 inches cubed. Example 2. A box is to be built from a rectangular piece of cardboard that is 25 wide and 40 long by cutting out a square from each corner and then bending up the sides. So if we cut out these 4 corners, and these are all squares, it says, and we folded up the edges, yeah, we'd get a box. So I'm going to label this an x by x square. Okay. Find the size of the corner square, which will produce a container that will hold the most amount of soup. Why are they putting soup in a cardboard box? Oh, cans of soup. Okay, that makes more sense. So most amount means maximum, and of soup, that'd be max volume. So let's think about volume of this box once I fold up the edges. So if we think about, if we fold up the edges, we're going to have a box How long will this side be? Well, when I fold up the edges, it's going to be from here to here, which is going to be 40 minus an x and another x. The width started out as 25, but I folded up those edges, so 25 minus an x and an x. And the height of the box would be this height of the edge folded up, so that's an x. So volume would be 25 minus 2x times 40 minus 2x times x. Now I really think this would be easier if it was multiplied all the way out. So 25 times 40, that's 1,000. And I'd have a negative 80 and a negative 50. That's negative 130x. Then negative 2x times negative 2x is positive 4x squared. Now I need to multiply everything by an x. And I'm going to write it in order because I am just that OCD. Now we're trying to maximize volume. So we need to take the derivative of volume. So I'd get 12x squared minus 260x plus 1,000. And we're going to set that equal to 0. I think everything is divisible by 4. So if I divide both sides by 4, get 3x squared, 65x, and that's 250. And 0 divided by 4 is 0. I think this factors. Let's see, 3x and x. I think I'm going to have 50 and 5. Ooh, that's going to work. 50 and 5. So it'd be a negative 50 and negative 5, because that would give me negative 50x and a negative 15x, which would add to be a negative 65. So 50 thirds and 5 are my options. So I need to check the number line. Let's see, 50 thirds, that's going to be bigger than a 5, so 50 thirds here. So I need to test some points. If I pick like a 1 and plug it into here, I'd have a negative and a negative. Something between here, maybe a 6, be a negative and a positive. And then something really, really big, I'd end up with a positive and a positive. So, positive to negative. Volume is maximized when the square is 5 by 5. This is 5, oh, they said centimeters, by 5 centimeters. And the reason we know that that's going to maximize it is because the prime of x changes from positive to negative at x equals 5. A rectangular page is to contain 24 square inches of print. The margins at the top of the page are to be 1.5 inches. So 1.5 inches for the text. And 1 inch on the left and right. So we've got this basically text box in the middle, right? What are the dimensions of the page so that the least amount of paper is used? Okay, what are the dimensions of the page? So, I'm going to call this X and this Y. So what do we know? Let's see, the dimensions of the page so that the least amount of paper is used. Least amount of paper. Least amount means minimum. And amount of paper would be minimum area of the paper. So that's going to be area, and the paper is X times Y. Okay. Oh, I got two variables. I have to do something else. it says the inches of print, this rectangle is 24. So let's see. The top and the bottom, they take off 1.5 and 1.5. So from here to here, 1.5 and 1.5, this would be y minus 3. And if I take off an inch and an inch, this is going to be x minus 2. So x minus 2 times y minus 3 is 24. I want to solve that for y. Oops, I need to add that 3 to the other side. So here's an expression for y. Maybe not the prettiest, but it'll do. I'm going to plug that in over here. And let's distribute. So 24x over x minus 2 plus 3x. All right. Derivative is next. Derivative of the first is 24 times the second. Plus the first times the derivative of the second, which would end up being a -1 in front, that to the -2, times the derivative of the inside, plus 3. I'm going to have to get everything to have the same denominator. I think that would help. Actually, no. What if I multiply everything by x minus 2 squared? Okay, what's going to happen on the first term? X minus 2, and one of these is going to cancel out. So 24 times x minus 2. Both of these will cancel out, so minus 24x plus 3 times x minus 2 squared, which is x squared minus 4x plus 4 equals 0. Let's pretty this up. 24x minus 48 minus 24x plus 3x squared minus 12x plus 12 equals 0. 3x squared minus 12x minus 36. Divide both sides by 3. See, 6 and 2. So x minus 6, x plus 2 equals 0. X equals 6, x equals negative 2. That doesn't make sense. X equals 6 does. And we could check it. 0, 6. If I plug in a 1, have a negative and a positive, which gives me negative. This would be positive. So the area is minimum when x is 6 because A prime changes from neg to pos. So what are the dimensions of the paper? 6 by 4, 9. Notice that the only part that was actually calculus was this step. Everything else is algebraic. So these problems really, the algebra is going to be what hurts you. I hate to tell you. And it's going to take a lot of practice. So we have a rectangle here, bounded by the x-axis, y-axis, and the graph y equals 3 minus a half x. What length and width should the rectangle have so that area is a maximum? Well, let's see. The area is going to be, so when we have a point here, that point is xy, right? Some x, some y. So the area is going to be x times the y value, x, y. Oh, two variables. Oh, luckily I already have something that represents y. I'm going to distribute just because that makes it look prettier. So 3x minus a half x squared. To maximize, I need to take the derivative. And I get 3 minus x equals 0. X equals 3. If I pick a 1, it's going to be positive. If I pick like a 5, 3 minus 5 is negative. So the area is maximized at x equals 3 because A prime changes from positive to negative. And then it asks what length and width should we have. So we have the length, it's 3 by, let's see, 3 minus a half of 3. Half of 3 is 1.5. So 3 minus that is going to be 3 by 1.5. Last type you might see. determine the point on the line y equals 2x plus 3, some point. And that point's going to be an x and a y. So that the distance between the line and this point is a minimum. So we're minimizing distance, which distance between 2 points is going to be distance formula. So x minus x, so x minus 1 squared plus y minus 2 squared. Two variables. Oh, I know what y is. So y is 2x plus 3. Now, just to make it easier, I think I am actually going to multiply the stuff on the inside out, to make it prettier. X minus 1 squared is x squared minus 2x plus 1. This is going to be 2x plus 1 squared. So that's going to be 4x squared plus 4x plus 1. So I got 5x squared plus 2x plus 2, when I combine like terms, to the 1/2 power. Derivative. Half comes down. Subtract 1 from the exponent, and then multiplied by the derivative of the inside. I could take, let's see, I'll write it out. It's going to be 10x plus 2 over 2 square root of 5x squared plus 2x plus 2. Now, if I'm trying to figure out when that equals 0, the only time it equals 0 is when the numerator equals 0. So we're talking about when 10x plus 2 equals 0. That's going to be at negative 2 over 10, so 1/5. Let's check what's happening with d prime around negative 1/5. So if I plug in 0, I've got a positive. If I plug in something negativer, I get a negative. So the distance is a minimum at x equals negative 1/5 because d prime changes, neg to positive, and it asks me to determine the point. So I have my x value. I just need the y value that goes with it. So that's going to be negative 2/5 plus, turn that into 15/5 just to make it easier on myself, 13/5.